Start. Okay. So now we
Okay,
start with the third lecture of Sakura, please.
good. Okay, thanks very much. So we will start lecture 3 like we started lecture 2 with sort of a reveal of the question I asked at the end. So the recap from lecture 2 is why I asked you to look at these T5 or Tn theories generally. So Tn were these essentially triangular toric diagrams, and N was sort of, these Tn theories, if you know class S, when you reduce them on a circle, you get the trinions in class S. That's why they're called Tn. So these are the 5D appearance of the trinions. And so the toric diagrams, now actually what I've drawn here is a bit more elaborate than just the toric. The toric diagrams are just these ones here with the vertices given by all these dots. So the question was, write down a resolution of this. So we have just the empty triangle. How do I resolve it? I place in the internal vertices that resolves the divisors. I introduce compact divisors. And then I also need to then include curves. And so what I've shown here, right, so if these compact divisors, this is for the T5 theory. So this is basically an example of which it's nice because it's slightly larger, so a little bit more happens here. All these curves here, right, connect to the external points. And in fact, what I've drawn here in these numbers is what we calculated. I gave you sort of the rule how to calculate these. These are really, whether these are -1 curves, so these are hypermultiplets, or these are actually -2, 0 curves. And since the intersections between, so really the curves are these connections, right? I draw them sort of on the edges, but really I should be drawing them on the lines. But it's these divisors intersected with this compact divisor that gives us that curve, and it's a -2, 0 curve. And these ones are the hypermultiplets, and these ones are the flavor cartons, if you want to say so. And how they intersect, in fact, tells us also about the flavor symmetry of this theory. So, for example, here we have a pattern of -2, 0 curves intersecting in this way, and then connecting to these hypermultiplet matter fields. -1 appear in here. So here we expect that we actually get from this AN diagram the AN flavor symmetry. In fact, we have 3 of these. So this is indeed for Tn, we expect an SU5 cubed, or for T5, SU5 cubed flavor symmetry. So one other thing I said, it would be nice for these more complicated things to actually write down rulings, and I sort of color-coded here the ruling, really the ruling which gives us the non-abelian gauge symmetry enhancement. This is given here, this is the ruling for this collection of 1, 2, and 4 vertices. So that gives us an SU4, and then this here gives us an SU3, and then there's an SU2 factor. And in fact, because there are also curves connecting the SU4 gauge nodes and the SU3 gauge node and the SU2, these are bifundamental matter. So what we're actually getting in this case are these quivers, and the flavor on this side here is given in terms of the -1 curve plus the flavor roots. So in fact, what we get here is a 5 flavor symmetry, so 5 flavors for the SU4, and then on this side there's just one, there's a there's this -1 curve, and in fact we can add the root to this, so we get a quiver with flavors 5 and 2 on either side. And now one other thing that we talked about yesterday was, so I can take one of these -1 curves and essentially flop them, right? So this -1 curve is really this curve here. And if I flop that, so I just retriangulate this parallelogram, I get this diagram here. So the curve, this curve here, I flop and get this curve here. So in fact, what the intersection numbers, how they change is that this one here, which is a -1. Now we can recalculate what the intersection of this one is. Well, this line here is the sum again of these two. So that's a -1 curve. And again, this line here is the sum of these two curves. So it's again a -1 curve. So in fact, we get two -1 curves. And so what you also see is that the curve that we had here is now not, right? So this non-compact divisor that sits at the tip here doesn't actually talk to any of the gauge nodes. So in that way, you've sort of decoupled the associated hypermultiplet from the theory. And indeed, this will be sort of decoupling it on the left. So you get from 5 flavors to 4 flavors. So it's nice in this slightly large example to look at that. And then the other thing I asked you to look into is the T3 example. So T3 was just this theory here. Again, I'm drawing it with the labels, right? So these are this is the -1 curve, and these are -2 curves. So what I get is this diagram here. Now we can do exactly these swap transitions. And in fact, it's a rank 1 theory, right? So we've got 1 gauge node, and then the number of flavors in this case is in fact 5. So this is a non-isolated toric diagram. Non-isolated because we have these non-compact divisors that come in and intersect the compact divisors. So this divisor here in the middle. And in fact, this should be the theory. That's the E6 Seiberg theory. And indeed, now doing this whole decoupling in the way that I discussed it just now over here, and here, you get this tree of theories, and you indeed get sort of, it's a slightly double counted way of getting to the full descendant tree. So it's not just a linear decoupling, because essentially here, the way you've arranged the flavors is the 5 flavors, normally speaking, you're really thinking of them as it's like an SU2 with 2 flavors on one end and 3 flavors on the other. And so it gives sort of different descriptions for, say, the theories with 4 flavors. Okay, so this is sort of the tree of decouplings, and you see at the end, we do reach this model that we had before. This is the SU2 with 0, and this is SU2 with pi, and this is the P2 theory. So indeed, from this T3, we can get all the way to the P2 theory. But there's actually no good other way of just writing in terms of toric models, the SU2 with more than 5 flavors. So the interesting cases being 6 and 7. Okay, and then maybe there's one other thing I wanted to say about this, which is if we go back to this story of the decoupling and also how this relates to Coulomb branch phases. So let me see. So in fact, if you look at this, right, so this is actually what I was saying before, you can think of the decoupling, right? So this is the T3 diagram, and then here we have the 3 flavors, the 2 flavors, and then we can decouple on this side, and we get to the 3-1. That's also 4 flavors, but equally get this here. And now you can ask, indeed, how does this now match with the Coulomb branch phases? And if we sort of go back, we discussed these decorated representation graphs or box graphs. And given, say, such a Tn theory, right? So you have now for Tn in general, you can imagine, right? So you scale this diagram up, you get n flavors on the side, and then there's an SUn minus 1 until SU2 with 2 flavors. So that's a general structure of the gauge theory description of these Tn theories. And so now we can ask, can we now reproduce this entire decoupling tree also from the Coulomb branch phases? And so sort of a slightly more feasible example. So we discussed the box graphs for the SU3 with 4 flavors. If you remember, this was one of the examples that we discussed. So for SU3 with 3 flavors, with 4 flavors, excuse me, we had here the SU3 roots acting, and over here the U4 roots from the classical flavor symmetry. And then also what we need is for SU2 with 2 flavors. In fact, we have an SO4 flavor symmetry, and the representation graph is just 2 of these 2 by 2 boxes, because it's really SO4 is SU2 times SU2, so you get SU2 here and SU2 here, and that's the second SU2. So this is gauge, alpha gauge. And over here we get alpha flavor 1 and alpha flavor 2 for the And why is that interesting? Because of course we can now use this box graph that we studied, the Coulomb branch phases, and for example they're relevant for the T4 theory, right? Because T4 by the same logic is 4 flavors with SU3, SU2, and 2 flavors. And so basically the consistent different Coulomb branch phases are given in terms of, again, blue is here the plus signs, and the minus signs are yellow. That's sort of just a nice way to quickly color code this. So what I'm drawing here is for the theory with 4 flavors, SU3, SU2 with 2 flavors, the Coulomb branch phases for each one of these 2 factors. So this is the one that we know that was one of the phases that we had discussed, and then this is actually a phase for the case with SU2 with 2 flavors. I'm not actually filling in what happens in the middle, and the reason for that is, in fact, there are many ways you could fill this in, right? So you know the rules that the plus signs propagate to the left, minus signs propagate to the right. So in fact, you could place here plus plus, minus minus, but you could have also placed plus, or you could have placed it like this. And in fact, these are different Coulomb branch phases that actually won't affect this is still just another, in terms of the phase, a different Coulomb branch phase. You're actually not turning on any other mass deformations. So if I'm interested actually in understanding the decoupling, we said we need to really change these boxes so that the number of flavor roots that appear here will change. So for example, in this case, we have to change, oops, what happened now? We have to change this box here or this box. And so this brings us to this case here. And in fact, in this case, we can also follow the whole Chern-Simons level. So if K goes to 0 at the top, then there are 2 branches and they correspond to the plus and minus a half Chern-Simons levels for the SU3 theory. And so if we follow this entire tree, you get sort of for the SU for this part of the theory for the SU3, you get this whole tree, and then for the SU2, there's a slightly small tree. Now you can combine these phases, and that gives sort of the decoupling tree for the gauge theory phases. And that's in general a subtree for in the geometry. Usually, what you get from these sort of considerations will in general be larger. There'll be more ways of doing these swap transitions. That's actually one thing I should note here. So in general, these swap transitions in the geometry are a larger set, right? Only contain the Coulomb branch phases. Right? Because there could be flop transitions, because there exist certain flops that do not actually respect the ruling. Right, so if you change the ruling, then actually you're not describing the same gauge theory phase, so not the phase for this particular gauge theory. But in the geometry, you could still do these transitions. So it's sort of really, most of the time, a strict subset. Okay, there was one other thing I wanted to say yesterday. Indeed, sort of these rulings are not unique. So perhaps this is something I should. So if you actually were trying to do this, you probably noticed this. So rulings are not unique. So if you did, for example, the Tn, there's sort of an obvious, right? You can rule it like this, or you could rule it like that. And of course, here there's a symmetry, and it gives you the same theory. But in general, they could be even distinct. So this is for Tn. In general, it could be distinct rulings that really give you different gauge theory descriptions. So for example, there's a nice sort of actually strictly toric, so strictly convex diagram. So if I look at this here, oops. So this diagram here, that's if I include the vertices here, the internal vertices, there's a rank 2 theory. And now I can try to put in rulings for this. There are sort of obvious rulings. There's one which goes along here. And I would say we get an SU3 theory. And now we could calculate the prepotential, compute how many flavors we actually, so the non-compact divisors, compute all the parameters. In fact, this is SU3, 0 with 2 flavors. But then someone else might have come across and said, well, I actually looked at it, and to me, I could also put in the rulings in this following way, right? So I can just first, it's still a singular sort of geometry, but I put in these 2 curves, and then these are curves of singularities. In fact, in that case, I get an SU2 theory. And now, of course, we will say, okay, so there are no more flavors on this SU2 theory, but then there's a question about the theta angles. And in fact, so these are the theta angle pi cases. So one way you could determine that is, again, for example, by inspecting this sort of, again, one nice criterion, like what yesterday someone asked, you could use the criterion of the one-form symmetry, right? Then in this case, you have no one-form symmetry, and so you shouldn't have one here either. But anyway, so in this case, you would get 2 totally different gauge theories. But the singular model, right? So if you just look at the singular geometry, so this object here, without any of the internal lines, and actually no vertices inserted either, right? This is one SCFT. So you would say that both of these theories in the UV, so both IR gauge theories have the same UV fixed point, right? Because the UV fixed point is this one singular geometry. And so this happens quite a lot. And whenever you have 2 rulings, right? So 2 ways of collapsing a collection of surfaces, you get such what's called a UV duality. It's a bit of a weird concept because essentially it's a bit different from what usual dualities are, but here all it means is there's one UV fixed point, and now you can deform away from that singular geometry or from the origin of the Coulomb branch in 2 distinct ways and get 2 non-abelian gauge series from that, or multiple. Okay, so that's sort of another thing I wanted to at least mention. Okay, so that's all I want to say for the moment in terms of the toric models. I will return to toric models tomorrow. So tomorrow we return to torics for the Higgs branch. So I don't want you to forget this, but what I want to do today, unless there are questions about the toric models, that would be a good moment to ask some questions. Now I want to go and discuss some methods that go beyond that, and that gives you a way to constructing essentially all 5D theories known to man or womankind. So are there questions about these toric constructions or what I just discussed in terms of DCB dualities, these phases, the decoupling, 30N. You're all good. So it can mean one or the other. So basically for today, what I want to do is sort of diffuse a little bit. I think there's a general sort of hazy understanding of, you know, how all these geometric methods, what's sort of the most general framework to study such singular geometries, and also what kind of tools are required to do so. And today what we'll do is, we already have seen, right, so that starting with the 61,0 theory, you can compactify on a circle, plus various mass deformations, right? So what we've seen in terms of decoupling, but also twists. We haven't discussed this, but there are also ways of acting with automorphisms to go to a 5D n equals 1 SCFT. So here we should also start with an SCFT. And so you might ask, then how do I actually do that in practice? Yes? So how do I describe the 60 SCFTs? The 61s, they suffer from the same sort of obstruction, that there is something like a Coulomb branch, so the tensor branch, but there isn't really a good way other than using geometry to understand the UV fixed points there either. So how do I actually go about this? And so here, what we have to do is remind ourselves that the 60 series are really obtained by geometric engineering construction, which is F theory on an elliptic fibered Calabi-Yau threefold. And again, non-compact, because we're not interested in coupling this to gravity. So what's an elliptically fibered Calabi-Yau threefold? Well, it's a relatively simple, it's sort of the most sort of probably structurally well understood class, if you want. So you have a T2 or an elliptic curve, and you have a Y3, and there's some base B2. And in fact, thanks to the work of Heckman, Morrison, Waffa, and collaborators, we know exactly what the B2s are. So in fact, to get a 60 SCFT, the base manifolds are essentially, and the possible fibers above them are sort of essentially comprehensively understood. There are some subtleties in the refinement of this classification, but for our purposes, I think we can say that the bases are essentially C2 mod gamma, where now gamma is in fact a subgroup of U2. So here's a note. If gamma is a subgroup of SU2, C2 mod gamma is in fact itself, it's a non-compact K3, so it's in itself actually Calabi-Yau. In fact, this engineers the 62,0 theories, and in this case, the T2 fibration is trivial. Right, so you cannot have a non-trivial T2 fibration over something that's already Ricci flat Calabi-Yau, because there's always, if you have a non-trivial fibration, in fact, there's at some point a singular fiber, so the torus degenerates, and so you will get some contributions from these singularities. Okay, so the interesting case is really when we have some, sort of, you know, the case when the base is some non-trivial. It could also be C2, but then there could be some other fibration over it. So let me actually explain when do we expect such a geometric object and to have a 60 SCFT underlying it. So the way this works is, so I can describe the 60 elliptic fibrations in the following way. So we'll assume, so for the experts, we assume that there's a section, so such fibrations are described by a Weierstrass model or something equivalent to that. So that's the following type of equation. Right, so the way you should think about this is there's a cubic and you have two sheets and two cuts and you glue them together, and so that's how you get a torus. Now, you more generally, of course, I want to think about this in terms of some fibrations. In fact, F and G here are functions or sections of line bundles over the base of coordinates on the base. And so in that way, this torus, this elliptic curve, varies over the base. Now, the fibration, if it's non-trivial, so the T2 fibration will degenerate. So the torus, for example, pinches off one cycle. So you go from something that's a nice smooth torus to something that's like this, and can further degenerate. And in fact, it will degenerate at loci in the base and above subloci in the base. So you have essentially the base B2, and then there'll be some sublocus, so U equals to 0, and above that you get one of these sort of pinched geometries, right? Where at the generic point you have a smooth fiber, but then there'll be subloci where it degenerates. And that's exactly, so this happens above delta equals to 0, and where delta is the discriminant of this equation we wrote down. So F cubed plus 27G squared. Right, and so F and G are functions of the coordinates in the base, and so this equal to 0 gives you a complex one-dimensional sublocus in the base. So this delta equals to 0 is a complex codimension 1 locus in the base. And what can happen, what kind of degenerations exist there? So how does torus degenerate? It's classic algebraic geometry. So this has been classified for surfaces, but it's true also in higher dimensions. So in fact, the types of degenerations of the fiber, they're classified in terms of a Kodara classification. And for what we need here today is, you could think of this as, it's morally speaking like an ADE classification. So how do you actually classify this, just to get an intuition for what it means to say, you know, what kind of degenerations are there, what's an AD classification in this context? What it means is that locally, right, where the fiber is singular, again, you can try to resolve the singularity. And so these fibers are resolved by essentially popping in P1s, and the resolution fibers are collections of P1s, so rational curves intersecting in the ADE diagrams. So for example, in fact, the affine. So this is affine. So the key here is that it's affine as long as you're in 6D, so you have a fully elliptically fibered model. And essentially this Kodara classification, so people will draw this as, so if this is a P1, then you get, for example, for an AN fiber, something like a collection of these curves intersecting in this affine AN thinking diagram. And then there are also D and E types. Okay, so this is actually what I just told you is sort of what is the vanilla version. These are sort of nice fibers, but you have just the torus, it pinches off and you can resolve it. And in fact, if the space is Calabi-Yau to start with, you can resolve these in the Calabi-Yau way by just inserting P1s. Now, that's not what we're interested in for 6D SCFTs at all. So this is the boring part. What we're really interested in, so to get a 6D SCFT, right, we don't just want some ADE fibers. And in fact, the dictionaries and the ADE fibers essentially will give you some ADE gauge groups in 6 dimensions. What we are interested in is in 6D to actually find particular loci. So the 6D SCFTs are in fact engineered when you have a Weierstrass model, when F, G, and delta are precisely not falling into this Kodaira situation. So, and that's exactly happening when at this locus delta equals to 0, the vanishing orders for these is greater or equal to 4, 6, 12. So this is what's called a non-minimal singularity. Right, so this is sort of, if you go to Wikipedia, open the Kodaira classification, at the very bottom of it, it says, and if F and G and delta vanish to more than 4, 6, 12, that's non-minimal, we won't discuss it, right? So this is beyond the Kodaira classification. And the reason is, and why is that? It's basically because you cannot resolve these by inserting P1s in the fiber, right? So you can, right, as I said, for many of these situations, you can, for these standard Kodaira situations, you have to resolve it, you put in collections of P1s, and then above this locus, this where the fiber was singular, well, you replace it by, for example, some affine ADE thinking diagram, which is given by intersections of spheres. Right? So you get a bouquet of spheres that sits above U equals to 0 here. But you can't do this if the vibration is non-minimal. So non-minimality means you need to resort to something else. And in fact, there are 2 things that you can resort to. You have to resolve it. Either you need to modify the base. Right? So for example, so these non-minimal singularities are in fact something we are interested in. We'll see in a moment why, in the context not of codimension 1, but actually at points. So you can blow up the base and then get points replaced by curves, and then you get a minimal vibration once you do this often enough. Or you can resolve it by inserting compact divisors, so surfaces, complex surfaces. And so the fiber then isn't just a complex one-dimensional object, so a complex torus, but its particular loci, it can then resolve the geometry by including a compact divisor that smoothes this too. So this is sort of the characteristic. So you do either this or you have either this option of blowing up the base or blowing up the fibers by inserting a compact divisor. And that's what's called a non-flat resolution. So in physics terms, what this actually is, so, I think we are all on board that the physics is why we are here. So in physics terms, you probably have seen people discuss for 60 SCFTs, the tensor branch. So this actually, this blowing up the base, this is exactly going to the tensor branch. And in fact, this also allows you to essentially show that these base manifolds have to be of the type C2 mod gamma with gamma in U2. Resolving by inserting these compact divisors, in fact, this spoils to some extent the structure, that you have an F theory, that you have secretly this dualton. And so here, actually, what you're really trying to do is you resolving this is more of an M theory picture, M theory dual picture. So that's where we come in for the 5D.
So can I ask a question?
Yeah, absolutely.
Yeah, so in the first case, when you blow up the base, I guess with the fiber, you're also inserting like a compact divisor, right?
Yes, so indeed. So let's be actually specific. So in the blow up in the base, so what you're actually asking is, so how exactly are we going to do this? So the point is, for 60 SCFTs, these non-minimal singularities occur in codimension 2 in the base. Right, so you have some elliptic. Let's just draw a picture. We have this is the base B2, and you have some. This is some component. So say U equals to 0 and V equals to 0 are both loci where delta vanishes. Right, so these are places where there's some non-trivial Kodaira fiber above. So here's U equals to 0, and I don't know. You have some singular fiber here. So you have some whatever. For example, let's pick EA because that's what we're actually interested in here. And V equals to 0 could in fact be a smooth fiber. This could be a smooth thing. And then at U equals to V equals to 0, we want that U equals to V equals to 0, that F, G, and delta have bigger than 4, 6, 12. And now what you can do is indeed, you can now write what option 1 is, blow up the base. It means you have these two loci, and so and now you insert at this point here a curve. So you separate them.
Right.
And then you have a P1 inserted here. And in fact, in this situation that I've drawn, which is in fact equal to the E string, that's why I'm drawing this. This actually is a -1 curve, right? So this actually is a self-intersection -1 curve. And so you might have seen that the E string indeed is just drawn as a -1 curve in the base. Now you still have, right? So at this point, I still have above U equals to 0 an EA singularity. Yeah. So you still have to, if you fully want to resolve this, resolve the E8 singularity, right? But that's a standard in codimension 1. This is Kodaira stuff. I think this was your question. You then still need to do some resolution of this E8 if you want to really construct the full smooth geometry, right? But
okay.
the thing that we had here, this point here, U equals to V equals to 0, non-minimal, you cannot remove by just blowing up the fiber if you're just inserting P1s. That's the point. Okay, but
okay.
once you separate these, right? In fact, in this case, each one of these intersection points is not just minimal, so it's standard Kodaira, and then we can just apply the machinery of Kodaira and resolve it. Okay.
But in the second case, sorry, yeah.
Now, in the second case, okay, let's get to the second case. So the second case is, so now non-flat resolution. Right. In fact, what we're going to be doing is you have U equals to 0, V equals to 0. Right. And now above here, there's still this E8, say, and here's a smooth fiber. And when they meet here, there was a singularity, but now I can insert, so the fiber here that I insert is actually a surface. So a complex surface. In fact, in this case, I can insert the various things I can do, and those will correspond to different theories in 5 dimensions. So the maximum I can do is I can insert what's called a GDP 9. Forget the G if you don't know what a Gen is. So a DP9 surface. So you insert a compact surface at that point. So the fiber isn't, so the fiber is a one-dimensional fiber, and then above that point, it becomes a complex 2-dimensional, and then everything else is again complex. That's why it's called non-flat, because it's not a flat vibration. Dimension changes.
I see. So
now there is a geometric transition from this DP9 to this picture here, right? Also, these are flop related, right? You could now blow down the P1 and blow up back the DP9, and you could go back and forth, right? Because above this P1, there's also fiber. Oops, oh gosh, this is not what I wanted to do. Right above here, there's also a torus fiber still. And now you could do geometric transitions and go from one to the other.
I see. So you mean the first case is a flat vibration over the subtional P1, but in the second case it's non-flat.
That's right. So here, right, because we insert above U equals to V equals to 0, we insert a 2-dimensional, 2 complex dimensional fiber. So this is what's called non-flat. Yeah, and the 2 cases are related by flop transitions. Yeah, but they have very different interpretations, because you can in F theory, the fiber is not actually a space-time direction, right? It's just the axial-dilaton direction. So you can still in type 2b, where the space-time, right, the compactification space is B2, you can still go into this tensor branch by blowing up this and inserting this P1, right? That's why in 60 you can go to tensor branch, and that's sort of a nice way of studying that resolution if you want to stay in 60. In fact, for us, it will be very useful to use this perspective of inserting here at this point a complex surface instead, because if you look at this picture, in fact, right, this is now a non-compact Calabi-Yau threefold. There are no compact divisors before we resolve. And in fact, by resolving this non-minimal singularity with one compact surface, you in fact, that's the compact divisor that gives you the gauge, sort of carton of the gauge group, right? So that's what we used to call the S, the surface is S, right? In the lectures before. And one advantage of starting in 60 with the 60 elliptic model is that in fact, these guys here generally will be the flavor symmetries. So the flavor symmetries will then be manifest in the description, and we can just essentially read that off from the geometry of these compact, from these non-flat fibers. Okay.
Okay, thanks. Okay, yeah.
Cool. Yeah, please ask questions. This is really good. It gives me some feedback as to where we are. Great. So this was sort of I gave you this specific E8, but it doesn't have to be E8 and smooth. This could be this is just an example. More generally, what you need to engineer is in codimension 2, this higher vanishing order of Fg and delta. So one thing that I always find people find a bit mysterious when talking to F theory, so people who spend a lot of their time doing these kind of resolutions, is how to actually do these resolutions. And since this is a school, I at least want to give sort of one example of how you do such a resolution and how you detect that something is still singular and how you actually pull it up. Because in toric geometry, it's quite straightforward. You just draw in these lines and put in points and that and so on. But once you're faced with a complicated equation, you might not know so much how to do that. And in fact, the example I want to study is, it's not quite an elliptic model, but actually it's a nice example to study, just to get sort of a feeling for how this works. So this is sort of an interlude, how to blow up singular hypersurfaces. Yes. So the case that I want to discuss, it looks almost like it's basically an elliptic model. I just want to look at sort of a hypersurface given by a polynomial. Hypersurface means one condition. We want a three-dimensional geometry, so we want 4 coordinates, and let's look at the following. Right, so this is a hypersurface in just C4. This is not don't think of it as an elliptic model yet. It's just to give you just an interlude. And the claim is this is a singular geometry. In fact, it's an isolated canonical singularity. If you want to see more examples of that, Xie and Yao have a nice paper where they tabulate them essentially. And we've recently studied the resolutions. So if you want to look at more examples of this type, I invite you to look there. So why is it singular? So singular means, well, there's a point X in C4 such that P of X is 0. So it sits on the hypersurface. That's the start. But then also the derivatives vanish. So the tangent space is ill-defined. So in this case here, in the above example, so for our P of X, that's clearly because we have the vanishing orders 2, 3, 6, 6. If I take the first derivative and set each one of the coordinates to 0, is singular at the origin. So now what do? We want to now resolve this, and we want to resolve this in a way, so the goal is resolve the singular locus by introducing a complex divisor, but in a crepend way. And crepend, if you remember, just means that we're keeping it Calabian. Right, so what it means is that once we resolve it, the canonical class still stays 0. So we have this hypersurface as a point, it's singular there. We want to remove this point and replace it with some compact divisor, right? So these resolutions usually introduce divisors. These are these exceptional divisors. So we have this point X equals to 0. And now we want to insert something at this point here, some PN or something. So with N1, N2, N3, some projective space such that it is smooth and the point X is gone. So basically the way to do this, and that's sort of the general rule, is you just remove the point by stating, so replace X equals to 0 by making the coordinates x1, x2, x3, x4 projective. So basically saying that they can vanish at the same time. That's sort of, it sounds like a brute force way of removing the singularity, but in fact, that really will do the job. So we remove, so basically we're saying x1, x2, x3, x4 are projective coordinates. And in fact, we need to be a bit careful that we can't always, depending on what these powers, in this case 2, 3, 6, 6 are, we might have to actually take weighted projective space. So in fact, so these are, so xi cannot vanish at the same time. So in fact, in this case here, to get, and that's sort of one condition, and then the Krappan condition resolution means, so I will insert these new coordinates. So basically, and I need to do what's called a proper transform. So kx tilde will normally go to kx tilde plus some over the exceptional divisors, right? So these are the blow-up divisors. Let's just call them blow-up divisors. And we don't want this contribution. So in fact, it means we need to divide the equation by the contribution to the canonical class of this exceptional divisor, by the contribution of dEI to K. And so in practice, it means if we have blown up with a P with degrees D1, D2, D3, so that's the generalization of P2, then we have to divide by the sum DI minus 1 power to EI to that power. So, okay, so let me actually introduce some, let's call this here delta. So delta is basically the coordinate. Delta equals to 0 corresponds to this new exceptional divisor. And so we need to divide this equation by this power of delta. So let me actually move this down here and write this out. So the proper transform, or the Krappanness of the resolution is guaranteed. So resolution is Krappanned if we can divide the equation by this power of delta. So let's actually consider this in our case. So in our situation, we had the equation was x1 squared plus x2 cubed. What are we doing? X3 to the 6, x4 to the 6. And in fact, what we want to do is insert a p 3, 2, 1, 1. Sorry, so here I'm missing d4. This depends on how many dimensional inequality L is. So what we actually get is we want to scale these with these powers, and if we do this, what it means is I replace x1 by basically each of the xi by delta. So this delta is still this exceptional projective space, and I'm inserting delta to the xi times delta, and then I need to divide by the suitable power given here. So in our case, we need to divide by the power 6, and 6 delta to 6. And indeed, if we insert this into here, so sorry, here should be the di's, then in fact we get x1 squared delta to 6 plus x2 cubed delta to 6 plus x3 to 6 delta to 6 plus x4 to 6 delta to 6. that's 0, and I can divide that by delta 6. So indeed, I can do the proper transform. And now this is the new equation. So in fact, in this case, the equation looks exactly the same, naively, as before. But the key difference is this is now an equation in C4 blown up at x equals to 0, where there's now a P3211 inserted. Right? So x equals to 0 is removed, and we've inserted this projective space. So in fact, the singular locus is now gone. Now we can calculate in this particular case what this delta equals to 0 compact is, a compact divisor. And in fact, this is a degree 6 hypersurface in P3211. So in fact, this is what is known as a DP8. So in fact, we get here a model where the geometry was singular, and then we blown up when we got in a DP8 surface. So we would say, so next you need, of course, check that the geometry is smooth, and if not, repeat. Right, in general, you would have to continue now doing all these blowouts. In this case, in fact, it's smooth already, and that's thanks to the fact that this was actually a very nicely chosen isolated singularity. And in fact, this is actually already a model. It's a DP8 surface. This is actually a model for the rank 1 EA theorem in 5D. But the problem is that because it's isolated, in fact, you see nothing of the nice flavor symmetries and so on. So in fact, to really get a handle of what, so the structure is starting with 6D, right? Starting with the elliptic model. Essentially, we do the same thing. We resolve the singularities in the same sort of way, replacing wherever it's singular with some projective space. What I want to do is to give you now the construction of this rank 1 E8 theory using the elliptic model, the F-theory model. So basically now let's return to the elliptic vibrations from 6D F-theory models. And let's consider the E string. So the E string I already hinted at is basically in codimension 1. So the base actually is just C2. So that's an allowed base for the 6D models, right? That's actually a very nice class of theories which just have a smooth C2 base, the very Higgsable models. So in codimension 1, we want two types of singularities at u equals to 0, say, so C2 has coordinates u and v. At u equals to 0, I want an E8 singularity, and at v equals to 0, it's just smooth. Weierstrass, so this is usually what's called I1 singularity. So it's just a node that degenerates into a node, the curve, so there's no actual singularity there. But then in codimension 2, at u equals to v equals to 0, what this actually entails is that it gives you a non-minimal singularity. Okay, and so one way I said is to use a Weierstrass model. If you are an F-theory practitioner, you know the Weierstrass models can be quite tedious. So if you actually ever have done the computation, you will have migrated to using what's called the Tate form. So Weierstrass, for most purposes, is nice, and it's perfectly fine. It's just, you know, if you have just F and G, then very often you need to tune F and G to get a certain type of singularity. And it's sort of, for most purposes, it's equivalent to using what's called the Tate form, the Tate model. And the key difference is that the Tate model. It looks almost the same, but I'll tell you in a second why it's slightly more user-friendly, which is, so it's again an equation. It's y and x being the coordinates for the elliptic curve, and has some coefficient functions, bi. And now these bi's, I will have some vanishing orders. So the vanishing orders alone fixes a Kodaira singularity. Right. So if you've ever used the Weierstrass model, so for example, if you have an A-type singularity you want to construct, F and G have vanishing orders 0, but delta has to vanish a vanishing order n for an SUN. So what it means is, right, because delta is not just FQ plus delta G squared, you need to tune F and G to very high orders to actually get such a cancellation in delta. And the advantage in the Tate model is that basically you can just fix the vanishing orders B1, B2, B3, B4, B6 to be 1, 2, 3, 4, 5 for an SU5, for example. So it's much simpler to use. Anyway, so this is why I'm using that model rather than the model that you might have heard, at least in talks people use. So how do you construct the E string? The E string is basically for the E8, it means along U equals to 0, the vanishing orders for, so the order at U equals to 0 of the BIs has to be 1, 2, 3, 4, 5, and for the I1 it be equal to 0 is just 0, 0, 0, 0, 1. Okay, so this is sort of what we have, and then at U equals to V equals to 0, the BIs actually have vanishing orders 1, 2, 3, 4, 6, and that corresponds to non-minimal in the Tate model. So that's the 4, 6, 12 condition for the Weierstrass model. So how are we doing in time today? Okay, so I'm actually running somewhat late. So now what we have to do is resolve this geometry just in the same way as what we have done. And I just want to sort of give you, I'm not going to go through this in a lot of detail, but I wanted to at least for completeness give you this example. So if you feel like this weekend you don't have enough to do, actually what happened? Okay. This is certainly a fun activity that I can recommend to do this resolution, to get a feeling for how that's done, because you won't learn this unless you've actually done one of these yourself and seen how it works. So basically, the geometry that we start, can you see this? So the geometry that we start with is this one here. Right, so in U, it has the vanishing orders for E8, and V only appears here. And now the notation here is basically any of these brackets. So X, Y, U, and then U1s. So this is always the exceptional divisor. And this is the locus where it used to be singular. So these become projective coordinates. Right, so here we're basically inserting a projective space with the homogeneous coordinates X, Y, and U, thereby removing a singularity at X, Y, and U equals to 0. And then as that's sort of the first step here. Right, so this basically generates that exception divisor U1 equals to 0. And then the next blow up uses X, Y, U1, and the next one is U2. So the last entry is always the exceptional one. And later on, there'll be also resolutions of this type where you have just 3 coordinates. So in this case, what this means is we're just inserting a P1, U10, U12 as a P1 with the associated exceptional coordinate U14. Okay? So basically, this gets chucked into 3.13, and at every step, there is a proper transform. So correcting for the fact that, in fact, we need to divide by this power of delta, in this case, U1 and U2 and so on. And at the end of this, I'm sparing you the result of the equation. All you need to know is the resolution. And this generates a surface. In fact, this case, for the E string, for this particular blow-up, this generates a Del Pezzo 9 surface. In fact, it has the collection of curves, which is shown here in this diagram here. So the key thing to note is the way you should think about this is there is a surface, right? This is the surface, this is the GDP 9, and the G is just saying we're using a slightly different complex structure from the standard Del Pezzos, namely they're related to standard Del Pezzos by flocks, but these Del Pezzos have actually -2 curves. And the -2 curves, as we now learned painstakingly in the last 2 lectures, are key for us to detect. For example, if there are -2 curves obtained from intersection of compact divisor, in this case the GDP9, with non-compact ones, those are really the flavor curves. So these have -2 curves as opposed to standard Del Pezzo surfaces, and you will see that indeed here we have these -2 curves sitting in a collection of exactly an affine EA diagram, and then there's a -1 curve attached at the far end. And so this is actually the geometry for the KK theory. And I'll also give you, right, so the geometric intersection numbers, right, so from S cubed being 0, we read off it's P2 blown up at 9 points, and this is sort of intersection data. And so what I think that more than perhaps this super technical information, maybe the thing that you really want to take away with is it's the way that these resolutions work is the following, right? So this is really starting in 60 how we can now engineer certain compact divisors or surfaces in these singular models. So in this case, this is a GDP9. It contains the full affine E8. That's actually the E string on a circle. That is, right, if you now collapse, you find a ruling of this is SU2 with 8 flavors. If we now actually do a different resolution of this geometry, we can also find the following situation. So again, the E8 fiber, right? So I said Kodaira along U equals to 0 just gives us an affine ADE Dinkin diagram fibered over U equals to 0. So each one of these curves fibered over U equals to 0. So each of these FIs, which are Kodaira P1s, fibered over U equals to 0, right? This is basically a non-compact divisor. Yeah. And now these non-compact divisors, they come in and at the locus U equals to V equals to 0, where we inserted this compact divisor in the non-flat resolution, that's now the point where this compact surface could in fact contain some of these -2 curves. So meaning contain means just that these non-compact divisors, d alpha I, right? So d alpha I dotted with S could be a curve, CI, and this could be a -2 or a -1 curve. And depending on what it is, it will contribute to -2 curves in the surface and thereby to the flavor symmetry, or it won't. So the example that I'm showing here is an example where I do this blow up, and this sort of changes, right? To get this particular blow up, you have to change the resolution sequence here. And there's a little bit of an art form to find the actual the resolution sequence that does that. When you actually look at the sort of all the possible resolutions, you can find compact surfaces that will have a sub-diagram of this EA diagram that contain the -2 curves are contained in there. And then there's always at the end attached a -1 curve that basically will correspond to hypermultiplets and will give us sort of the hypermultiplet plus then adding the roots, the full set of hypermultiplets for this theory. So the geometry, after we resolve it completely, has the structure of there are these non-compact divisors, right? These P1s, fiber of U equals to 0. There's one compact divisor in this case. This is S. So this is the compact surface. So this is telling us this is a rank 1 theory. And this, which of these curves of these non-compact divisors actually contain determinants of flavor symmetry. And in this case, the I1 isn't doing much because it's basically smooth. But later on, for example, you could tune this here to I2. And then you would be looking at the rank 2 E string. This will contribute an SU2 part to the flavor symmetry. Essentially, here you will have sort of an alpha and SU2 diagram. And that can then also be contained in this compact surface. So I hope this is sort of clear. I didn't go through this computation with you, but I think I explained how you should, if you have all this information, how you could now sit down, open Mathematica, chuck in 3.13 and do this calculation for yourself. Okay, so one thing I want to say, and I think we basically, yeah, we still have some time. Right. Exactly. So let me summarize a few things I said in words, because I think that's so important for you. So if the P1 is basically obtained in this way as an intersection, this is again a P1, and it has Ci squared is equal to -2 inside the alpha I, and Ci squared inside S is 0, then this actually is a -2, 0 curve that's intersection between compact and non-compact, and this will contribute to the flavor symmetry, flavor curve, right? And the collection of all such flavor curves and their intersections, right? Because these -2 curves can intersect with each other. They already come from this E8 fiber in our example. So they're intersecting right into an alpha and E8 Dinkin diagram. And that pattern will then determine the GF. And this actually is now the GF UV. And why is it GF UV? Because UV, because these curves, right, being contained in S, these curves will go to 0 volume also in the UV limit, right, when the volume of S goes to 0. Right? So strong coupling is collapsing the compact surface. So that's basically where we came from, but then in this resolution way, we see which curves are contained. And the -1 curves, right? So these are basically the hypermultiplets. Those are the ones that are basically the alpha i's that are contained in the alpha I dot S. I sort of, like, if someone wants to understand this better, please ask me. These -1 curves come from reducible fibers, right? I think we talked about this yesterday. So some of these these rulings can have reducible fibers. In this case, actually, one of the roots, in this case, F1, right, actually splits into a collection of 2 curves as you go to this point U equals to V equals to 0. And it splits into 2 -1 curves, and one of the -1 curves is contained in S, and so that actually will be the hypermultiplet curve. So these are contained, so they're not just the intersections of compact and non-compact devices, but are contained in that intersection. So these are coming from reducible fibers. And if an M2 brane wraps them, right, they become massless. So, and the mass of the hypermultiplied is sort of proportional to the volume of these C alpha I's. And so if we take the volume of one of these C alpha I's to 0, these hypermultiplied curves, that corresponds in going to a wall in the Coulomb branch moduli space. Right, so we can take in this picture that we had here, the volume of this curve, this -1 curve, right? So this is a hypermultiplied curve, and the other one, the -2 ones, are the flavor curves. This hypermultiplied, I can now take the volume to 0, so a -1 curve has a Kähler deformation to shrink it to 0 size, and then I can do a flop transition. I can blow it out so that it's not contained in S. So in fact, this is precisely now the decoupling process. Right? In fact, we can now flop this curve and so we blow them up. So the picture is right. We have this -1 curve. Maybe do some sort of cartoon diagram for that, but it's really in this geometry that from this resolution, right? You have a -1 curve, and this is S. I can flop this curve out of this, right? So this is if you sort of think of this curve as an intersection between some other divisor and S, it sits here, and I get another -1 curve, and then the mass of this one here is basically this is the volume of this one is the mass of the hypermultiplied, and I can take that to infinity, and that decouples this, and this gives us a new theory as prime, right? Because now that curve isn't contained in there anymore. But that's the analog in this context for these flops that we consider in the toric diagram. And in fact, the rule, so the general rule for flops is if you have a collection, say, of -2, -1, -2, -2 curves, and now you want to flop this one, and these are contained inside S, and you want to flop this out, then in fact, this affects the neighboring self-intersection numbers and the way that this becomes -1, that's gone, -1, -2, -2, and so on. We can discuss, I can explain what the general rule is, but that's basically, it comes from just analyzing how the flop affects the normal bundle and the canonical bundle of the surface and the curves. So this is the flop of -1, this -1 curve out of the surface of S. And in fact, once we realize that, in fact, we could start with, say, this E8 model, this affine E8 model. So this is the GDP9 model. And here we have this -1 curve. And now just start flopping this out of this. And then this one becomes a -1. And we keep doing that. And that should correspond exactly to the decoupling. And indeed, this is what we find. So in fact, we don't need to find a TOC, the resolution that now just has, say, E7, but we can just start with the marginal theory and then do the flop transition. So the main strategy is to construct 5D SCFTs from 6D SCFTs is basically do the non-flat resolution of the elliptic model, right, with its non-minimal singularity, and find here the non-flat resolution that realizes the KK theory So morally speaking, what this means is it contains basically the full, in most cases, this means it realizes it has the flavor curves for the 6D flavor symmetry. Contained in the compact, in the non-flat fibers, right? So for the E string, this was the GDP9 resolution, which had essentially the diagram, there's a -1, then we have -2, -2. Anyway, the affine A diagram and this -1 curve. And then as a second step, now flop the -1 curves out of the compact divisors. Right? So these non-flat fibers, these are the compact, the only compact divisors in the top one, and then we can just keep flopping them out. So let's actually consider this for the E string. Oops. And for that, it gives us the following. So this is the general strategy, but what I want to show you is how this actually works in terms of the E string. So the marginal theory, right? This was basically what I showed you before. So we have these GDP9, and this is basically the codimension 2 fiber that is contained inside the compact surface for this rank 1 theory. And there's a -1 curve here, and I can start flopping this. And so I flop this out, then I get this orange diagram contained, which is just now the A theory, and so on and so forth. And in fact, we also get all the way down to the 2 branches for the SU2 with theta equals to with 0 flavors and theta equals to 0 and theta equals to pi, as well as the P2 theory at the very bottom. Right? And so the strategy here is really just keep flopping these -1 curves, and there's some branching here, and at the end you just end up with a single +1 intersection curve, and that's the P2. That's the hyperplane class of P2. And so this actually is exactly the list of now all of the rank 1 theories realized in terms of actual geometric construction. So as a last thing now, this should have sort of whet your appetite and say, well, okay, so what I really need to construct is the geometry, the non-flat resolution with the compact surfaces for the marginal or for the KK theory. So I use these two things, just the KK theory. And then determine the -1 and the -2 curves, and the rest is completely algorithmic. It's just applying these flops on these -1 curves. So if you take one out, the neighboring one becomes a sort of sub-intersection increased by 1 rule. And so you can essentially take that problem and really reduce it down to that story, right? Just determine what is essentially this diagram here at the top and distinguish from that the -2 and the -1 curves. And so this is basically what we call these combined fiber diagrams are. And so I want to just so if you just really go to the bare bones of what we've actually discussed, is just take a diagram. So the only calculation you then have to do is one resolution for the top theory for this. This is the GDP9, right? And then we say we have -1 curves. These are the hypermultiplets. Those we draw, and then we also draw the -2 curves, and we can mark them in some color. Actually, let's mark them in green so that they're distinguished, because these are the flavor curves. And then I just draw the graph of these two sets of curves, how they intersect in the compact surface and for the marginal theory. And the subgraph of the -2 curves will correspond to the G flavor symmetry in the UV. And the -1 curves will tell us how we decouple hypermultiplets. And that's all we need to know. We can forget about the fact that it was a Del-Pezzo surface at that point. And we can read off many things from just this sort of structure. And so these types of things, they're basically called these combined fiber diagrams, or CFDs. And we now only discuss them for rank 1, but this now applies to, you can imagine, right? This applies to any higher rank theory as well. You just pick this resolution for the KK theory, and then you just descend from there. So one nice example to study is, for example, the rank 2 E string, right? And then, so this is the collision, if not E8 with I1, but with I2. The 60 model, so we have U equals to 0 in E8, and then we have a B equals to 0 in E8 and I2, and they meet at a non-middle point. Now we need to do a non-flat resolution. This is actually a rank 2 theory, obviously. So in fact, there are two compact surfaces. And what the diagram that we're actually interested in isn't so much as how they are distinguished between which surface contains which curves. It's really these, we're interested in the, let's call them S1 and S2. We're interested in the union of these to a reducible surface and determine the CFD, meaning the -2 and -1 curves for this reducible surface. Okay, and we can do this, and that's the last thing I will show you. I'll leave you with that today, and then we'll see what we will do tomorrow. This is sort of the moment when you either run or you sort of say, oh, okay. So this is, I hope you can see that. So that's actually the CFD for the marginal or KK theory. That's the rank 2 E string on S1. So you see there's a subdiagram of green curves that are -2 curves. That's an affine E8, but there's also an affine SU2. And so you read off, indeed, the E string theory in 60 has an E8 times SU2 flavor symmetry. There are two -1 curves that are here. And one can now start the whole flop chain, right? It's a completely, I really have a Mathematica notebook and just chuck it in and it computes all the descendants, and just drawing them out, you get from here all these connections of theories. And in fact, the flavor symmetries are read off from these green diagrams, and depending on what, so if we have these gray boxes, they're theories that are non-Lagrangian in the same sense that the P2 theory was not Lagrangian. And this matches beautifully with the sort of surface construction that was in the paper by Jefferson, Katz, Kim, and Raphael for the rank 2 E string theories, just in terms of the flavor, so how the models are connected and what also gauge theory descriptions they can have. So one thing I didn't manage to do today is to connect now this to the gauge theory description. So that's sort of the thing that maybe will take me still 15 minutes or something, but I hope I can fill in tomorrow, and then we'll go to the Higgs branch as the final sort of fun part. So are there questions about this? The last question I had was about the non-flat resolution, and I hope I didn't lose everyone from there onwards, but are there any questions about today's?
Can I ask a quick question?
Sure.
Yeah, so basically, I think you are just blowing down all the -1 curves. And then
Yeah, you're blowing
Yeah,
them
should-
down, but you're also, right, you're really blowing them back up outside of the surface. Yeah, so the
Okay.
process, you should really think of it as you really take this curve. This is a curve that's, say, coming from some intersection with some non-compact divisor. This curve, I blow it down, and then I blow it back out, right?
Right.
Right. So the standard flop chain is sort of the SU channel, right? So we've got some configuration like this, and then we go, it's a T channel. So this is the curve C, and this is C prime, and we really want to do this full flop transition. And once you've arrived, right, so that's the sub diagram. And now this curve here, you could still think of it as a hypermultiplied matter, but with massive high, but now I can send that mass to infinity. And that's the decoupling limit for that. I can sort of integrate this out, and then the resulting thing is a new theory, which is characterized by another surface S prime. Put differently, you start with a Delpezzo with n blow-ups, and then you just blow down this curve, but then you also remove it, because you're not just looking at the surface, but you're actually looking at the surface embedded into some Calabi-Yau geometry, as you really have to resolve it back out, and then you decouple it.
Okay, thanks.
Yeah, thank you.
Can I ask one question?
Sure.
Yeah. So for your rank 2 string theory, the Hfd diagram. So the first diagram, you get the first diagram by resolving the
this
singularity.
Here, that's right. So I get the first diagram by, I can actually show you exactly the equation, because we discussed the equation here. So it's now an equation where instead of v just to 1 power, actually, I think it's here v squared. And I think you might have to have actually, so you have to tune the I2 fiber slightly. But it might be that B4 also needs to be actually and has about power V. But this geometry, actually I don't want to change this here, this will be confusing. But this geometry I resolve in the same way. The only difference is that now I will have 2 blow-ups, which essentially are blow-ups between the U coordinate and the V coordinate. So it's like when you go to the tensor branch in 60, right? You remove U equals to V equals to 0 to introduce a P1 with -1 intersection, but that's still singular. So you resolve again, and so you see there's another curve, right? And so here it's manifest in the fact that you could in this non-flat resolution do 2 resolutions that involve U and V coordinates. It's very similar, it's just that it happens in the fiber. And so the diagram, I think you were asking how I get this diagram, right?
Yeah, the first diagram, the top.
This one here, right? This here.
Yeah.
So how do I get this diagram? So generally speaking, right? So the situation is, again, we have an E8 worth of affine E8 worth of D alphas, non-compact. But now also we have an SU2 hat. So this is rank 2 of, say, SU2 alpha, say, beta, also non-compact, right? Because now I have E8 and an SU2. And now I have...
sorry, this SU2 is...
So this is basically... Yeah, it's universal because I'm constructing. So in 60, I constructed by having an SU2 affine collided with an E8 affine. So that's basically just, even as a 60 model, elliptic fibration. And then at U equals to V equals to 0, so this is U equals to 0, V equals to 0, and I can resolve that, right? The picture looks basically the same as what it did here, except, so actually let me bring in the picture here and show you how I would modify it. I can just copy it in again, and I think this would be useful. So for the rank 2 case, what changes is, in fact, this here will be something like the two, there's a -2 curve, -2 curve, right? It's an SU2 affine. And so they collide, so this is rank 2. And they collide, and now what happens is, in fact, there's also now the question, there's still the SU2 fiber, are they also contained within S? And there's also, so S here is the union of S1 union S2. So for example, you would say, actually I have it here, so let's pick some. So for example, you would say the surface should be blow up 9F4 cup F0, right? So for example, there are many other ways you could write it as a gluing of two blown up Hirzebruchs or Dapetzers. I don't actually care which of these different realizations, they're all like related by flops of internal curves, right? So all I care for is how does this union of surfaces intersect with the d alpha for the E8, and I need the square, and what's intersection of with SU2 squared. And now given a resolution, right, it tells me, so this will give us some table of intersection numbers. And for example, these are for the alpha 1, alpha 2, alpha 3, alpha 4, and so on. If these are -2, -2, -2, it's 2s, and then for SU2, it's -2 and then -1. It means I'm already in a flopped phase. I've already flopped sort of that one of the, so I'm actually not in the KK theory anymore, but in the full theory. So to actually get the KK theory, I need all of these intersection numbers to be -2s, meaning roots of all the affine, these should be all affine, of the E8 affine, SU2 affine need to be contained. And that's the resolution. Once I have that resolution, I can read off the intersections of these, and then I get this of the -2 and -1 curves, and I get this diagram here.
Okay.
So, for example, there could be different realizations that, for example, where, say, one surface contains all of the E8 and the other one contains the SU2 or some part of the 8. I don't distinguish them because I actually want to just know what's the full flavor symmetry. And for that, it's only relevant that I know which curves are contained at all.